introducing Miguel Romance del Rio from the University of the King Juan Carlos in Spain, right? Who's going to present Parenclitic network applied to credit card fraud detection.
Thank you, Christian. Thank you also the organizer for letting me present my research here. It's a great pleasure to stay here and to be in contact. I'm coming from the Complex Network Society, the pure Complex Network Society, and so it's a deep honor to be in contact with the real world and find something apart from formulas and logarithms and things like that. So what I'm going to present here is a joint work with several friends from two of them from my university, another from Mallorca, and a couple of friends from Italy. And we have developed several works in this line with the collaboration with the INCIBE, which is the National Institute of Cybersecurity in Spain, the responsible of cybersecurity, our university, and one technological institute that where I belong that tries to put together the severe security problems with the tools coming from data science and network science in order to find some solutions. Okay. The main goal of this talk is presenting a new way of using network in order to represent data. Okay, so I'm going to show to illustrate this approach by showing how can we apply it to the credit card fraud detection problem. But my main interest is to present the method, not the results. I'm not expert in this area. I'm just a theoretical one, so I just try to show how to use it in a naive way. So in my talk, first I will introduce the basic topics about what is a Parenclitic, what is the problem, the credit card fraud detection. Then we will focus on the main part of the talk, which will be how to define these new Parenclitic networks. I know that is a difficult name, Parenclitic is something strange, but I will explain why it's appearing this name. And in the final part, I will make an easy application to the credit card fraud detection. Okay. The credit card fraud detection is a major problem. It's a real challenge, not for the financial system, but for the society. Because I guess that almost all of us has at least one credit card in our pocket right now. And we are using not only in a shop, but probably on the internet. And it's a big risk, and so the amount of money we are spending every day is a big challenge to find a way to determine what is illicit and what is a fraud. So the number of the amount of money it's costing is huge. It's the level of billions. So it will be interesting for a user to know that we have deep methods that try to catch and try to stop online this process. So I'm not going to go into a very big deep details about the explanation about this problem, because in the yesterday keynote speaker, the Professor Juan explained a very good approach to another problem which is very similar to this one, which is the money laundering. They are not the same problem, but they are almost twins. They are close, very close relatives. And so she explains in a very best way than myself the problem, so I'm not going to go into details on the peculiarity and the critical point of this problem. So, but just to point out where I'm talking about, there are two kinds of techniques involving the detection of credit card transactions. The first one is the classic one, at least in Spain for the most part of the banks, which is what I call the classic learning. Classic learning is somehow a set of rule-based and known patterns that we know, and they say, okay, if something happened in a transaction with this, and that, you have to stop. Why? Because of our past knowledge. And there is another line, much promising one, which is the machine learning techniques that tries to combining supervised and unsupervised approach to try to find out when a transaction is illicit or is a fraud, right? Okay, I'm going to focus on this second part. And my point of view is, can we use complex network to detect credit card frauds? That is, in a more general way. And this is the main topic probably of this conference. How can we put together complex network and data science in several problems related with banking and with finance, in this particular case of fraud detection? Along these 4 days, we have seen a lot of examples, many examples on every talk of how to use network on problems of machine learning and things like that. But roughly speaking, the use of networks in these topics, in a very complicated, very fancy, very clever way, can be resumed into 2 cases. What's what I call the physical network. That means we have a data set that has a proper network or a proper set of networks. For example, if we are studying transportation systems, the metro system, we have a network, physical network, the stations, the trains, whatever, and that's the network we have to consider. The second, a very long and very fruitful way of considering networks in machine learning is the functional networks. Along these days, we have many very good talks talking about functional networks. We have, so for example, temporal series, and we compute a network where every node corresponds to a series, and they measure the correlation between these 2 temporal networks. That's the case. Okay, I'm going to present a different approach. Another way to defining a network associated to a data set that measures not the correlation, but the deviation. It could be something similar, but it's not the same case. So what I'm going to use is the Parenclitic network approach. That means that we start from a data set, general data set, where we have some pre-labeled subsets. Let's see, for example, we are talking about medicine. We have a subject of subjects, of patients, and we have pre-labeled some of them that we know they are healthy. And for each patient, we have, for example, a blood test. Say, this is okay, this is healthy, this is healthy, this is healthy. I don't know this one. And we have to know, we are going to associate to every patient, healthy or not healthy, a network that says and that illustrates how far is it from being healthy, right? In fact, the word parenclitic, this strange word, comes from Greece, is something not very new. It comes from Epicurus. This philosopher talks about the parenklisis. Parenklisis is a term in Greek that means deviation, that explains how the atoms differentiate one from another and goes and start producing different matters, right? So parenklisis means the deviation. How far are you from being healthy, for example, right? And you associate to every entry in a dataset a new graph. Let's explain in more detail. I'm sorry, I'm a mathematician, I have to confess it. So I have to put some formulas. Let's start, for example, with a dataset G, where we have a subject or an element Ti with some feature vectors, and we have some subset of elements in this dataset that we have pre-labeled, for example, as healthy or sane. Okay? So we would like to construct a function h from Rd to R such that all the healthy patients are close to this manifold defined by h. Okay? That means that the healthy people are very close to a manifold. Now, this is a dream for a mathematician to find a function to this problem. Real life, impossible. You can do this. Okay? So in general, computing such a function is impossible. In fact, there is no function h in this way in the real life. So what can we do for this? We can project the problem into 3 dimensions, for example. If we have a data set with many dimensions, in this case 3 dimensions, 3 is enough, because plotting something in more than 3 dimensions is hard. And we have to project into several, and so instead of trying to compute this function h, we can try to compute somehow a kind of projection of this function. Probably is not possible because h do not exist. But in this case, we have 2D problems we can approximate, right? At this point, the green points are the healthy people, and try to approximate this hix as a projection of this h to be a function that somehow fits the points, right? And thereafter, when we do this for this couple of features, for all the projection, two-dimensional projection, right? And now we construct for every new patient, every new node, written here in red, a network where the nodes are the features. And the links between features, what is? Is the divergence between the real value and the supposed value for a healthy people, right? So it means how far are you from being okay, from being a perfect element, right? So later we will consider, in order to compute that, we are going to use, for example, linear regression. We can do something more fancy, but I'm just going to do it the first model, which everything as simple as possible. Then we construct the Parenclitic network for every entrance in the dataset as a network where the nodes are the features and the links are the distance between the supposed value and the real value, right? This is a weighted graph, of course, and we can convert it in an unweighted graph by putting a threshold. If we put a threshold, we will find something like that one, right? That's it. It's very easy, very easy to do it, but if we move this threshold, of course, we can find something different. If the threshold is 0, we have a complete graph, of course. If we have theta big enough, then we have nothing. And in between, what happens? Oops, I'm sorry. In between, we have, for example, this two situation. This is for another application of healthy, of some medicine problem, where the links, the color of the links are related with the weights. Green one means low weights, red one means big weights. So on the left, it corresponds to a healthy person. And on the right, it corresponds to a non-healthy person, right? One advantage of this method is that not only we can associate a network, but we also can spot why one person is healthy or not healthy. Because we can find where is the correlations that are very far from the original case, right? So this method was introduced 10 years ago, and it was not used for classification models. But what happened for classification model? Can we apply this? Yes, it was done for biomedical problems, and now I'm going to present an application to create crowd detection. So in this case, the method I'm going to use is we consider first the credit card fraud detection as a supervised problem. We can consider as a supervised plus unsupervised, but I'm going to use only supervised methods. Then we start with a data set, a labels data set where every record is fraudulent or licit. We compute some features, we enrich them with this Parenclitic network, and then we do a classic model of classification and see what happens if we only do the classic approach, the Parenclitic approach, or a combined approach taking into account the features and this new network. Okay. The data set I'm going to consider is a private data set of real transaction of a major bank in Spain. I'm not allowed to say what bank, but it's one of the 1 or 2 most popular banks in Spain, and it's not Santander, right? Okay, this data set includes all credit and debit cards in personal virtual between 2 years where it appears 15 million of operations, 7 billion of cards, and 40,000 transactions per month are fraud. So here we can see that this data set is tremendously unbalanced, right? The usual problem in credit card protection. It's a good idea, a good news for the users. Okay, so we start with, we select characteristics and we focus only on these 2 characteristics, rock features, the transaction size, the hour of day. We construct several other features related with every credit card. This all another 6 characteristics, very popular, all in euros, of course. And for this, no, this one. For this 8 characteristics, we construct the Parenclitic network of every transaction, right? Of 8 nodes. A big complex network of 8 nodes, not too complex, but a network. And we realize that they have some structural properties, that they are star-like, they are high clustered, high efficiency, low information constant, but we plug this network into a regular matrix classification network. So we can add directly, or we can compute several structural parameters. In this very naive approach, we only consider structural parameters, right? We compute these 7 basic structural parameters. The first 6 are very popular. The last one is the only which is not usual in the community. The information content is related with the modularity somehow. It's a variance of modularity. And we do the usual stuff, and we compare 3 scenarios. First, we only consider the 8 non-Parenclitic features, the classical one. Second approach, considering only the Parenclitic feature, mean degree, etc., etc. And a combined approach, taking all together. And what are the results? Well, we consider several classic and very naive methods. We consider multi-layer preextension, where the result we are going to show here. And this is the result. The classification error based only on the fraudulent transaction. If we only consider the Parenclitic, this is worst impossible. It gives a very high classification network. If we use the usual approach, of course, here in the x-axis is the length density, the influence of theta is constant. But if we combine them, we get something which is better. So what means? From a pure mathematical point of view, that says that the Parenclitic networks, that means the relationship between features, gives extra information to the system. We also compute the ROC curves, rating the true positive rate and the false positive rate, and find something that it gives something better, but not too much better than only the good features. Okay. As a conclusion and future works, I would like to have convinced you that this Parenclitic approach could be useful in some sense, that it helps you to understand not only the features, but the relation between the features, how far are from a usual way. They give complementary information. It can be useful to predict problems like credit card detection. We have developed another works. For example, we have computed not some parameter of the Parenclitic network, but the Parenclitic network at itself in a method of graphical neural networks, and the results are slightly better, but not too much. And we are also working right now in higher order network Parenclitic. What's this? Instead of considering relationship between couples of features, considering relationship between groups of features, right? This is the new fashion in complex network theory. Instead of considering graphs, considering hypergraph and simplicial graphs. And it's a very good promising result here, because in some data set we have tested, they appear 3-body and 4-body interactions that do not appear in a regular network one. And that's it, all that I wanted to say. Thanks for your time. And
questions for Miguel?
How do you select the subset S on which you build the regression and then compute?
Yeah, very good question. In this case, we made at random the selection of sets because the set is unbalanced. So we select several of them, we make an ensemble, and we get with all of them.
The dimension, the number?
The number, I don't remember, but as far as I know, it was 15,000 of illicit and 15,000 of, we take about 15 or 13,000 of legal or, yes, Ines.
Any other questions?
Thank you. In terms of what you mentioned about the hypergraph thing, what kind of, and you mentioned that you run GNNs in the graph regime you run GNN, right?
Mhm.
The hypergraph setting, what kind of neural network do you run?
We are done. We are didn't done. We have done the same approach that we have done here. So instead of putting the hyper network in the system of machine learning, we compute several parameters. We select the proper one, and we're at the point of finding something that it works better and works like a graphical neural network for high.
Actually, there is a model 2 years ago, probably was introduced, hypergraph neural networks. Maybe it's
Yeah. Thank you.
Well, let's thank Miguel once again.
Thank you so much.